Hello, my name is Colvin Geiman, and today I will be presenting my survey project that I did for Geology 360 Geophysics. So for my project, my survey, what I wanted to do was I wanted to find an area on NKU property where I could conduct my rock core collection. And the thing is that with the rock cores, we're going to be digging into the ground. But NKU does have a lot of underground pipes and drainage areas and even electrical wires that crisscross across campus underground. So what I wanted to do was use resistivity and GPR surveys to find out if there were any underground bodies on this section of this hillside here right outside the science building. As you can see, there are sewer lids which indicate that there is underground piping in this area. And I want to make sure that there is no piping coming across this hill here, because if there is, collecting survey cores on this side of the hill will be very, very difficult. My hypothesis for this survey was that there more than likely would be no drainage pipes going across this hill here, considering that there's a steep incline over here on this hill. And considering it's like a distance of like 20 feet from the top of the hill to the bottom of the hill, it didn't seem like there was any drainage pipes exposed anywhere that allowed water to come through. I also did not expect to find any groundwater in this area because we're on top of a hill. The groundwater is not going to be very, very high up here. I also noticed at the bottom of the hill that there was a drainage tile at the bottom. And I thought that these two, the drainage tile and the sewage lids at the top of this hill, probably were not related still because it seemed like too great of a distance, or at least too great of a depth for them to be connected. But I understood it was not entirely unplausible, so I continued with my survey. I used two surveys on this project, and the first survey I used was a resistivity survey. The resistivity survey was used to detect the resistive or conductive underground bodies on this hillside. I knew that if I could detect metal or water using this resistivity survey, I would be able to come up with one of my conclusions. The resistivity survey was great for detecting metal and water because metal and water are both conductive bodies. So if I found something that was highly conductive, I knew that I would be able to detect the pipes coming through the hillside. The equipment that I used started with the laptop, which was prepared using a Warner array. The Warner array is the deepest resistivity survey that I had available. And I chose that because, of course, being on top of a hillside, I wanted to make sure to be able to get the greatest depth as possible. The Super Sting is this golden device here. And what it does is it receives the electric current coming from the wire here. It receives that current and translates it into data. And what it will do with that data is that it will create an image of the underground area along this cross section here. That then gets displayed on our laptop, and we're able to make an interpretation based off of that. We have a battery connected over here, which is connected to our Super Sting. And what it does is basically powers everything and makes everything run and work properly, as well as provides our electric source to create our survey here. This switch box here is connected to the Super Sting, and what the switch box does is it allows us to be able to create multiple surveys at one time. So switch box, for example, like the survey that we have here, it can create a two-dimensional survey, or it can create a three-dimensional survey, which would be perpendicular to this, creating an image that would help us be able to better visualize this underground area on a three-dimensional scale. And it can even go up to four-dimensional, which is pretty cool. But for this survey, considering we're only dealing with this row over here, making sure that these drainage pipes aren't extending through the hill across, we just stuck with a two-dimensional. Now, of course, you can see all these wires over here. These are wires which have conductors on them. You can barely make out, there's a black dot here, and that is the conductor. Basically, what these wires do is they send electrical current through the wire and transport it to these conduits. And what the conduits do is then send that electric current down into the electrodes, and the electrodes transmit that current down to the ground. What certain electrodes will do is certain ones will turn on. So for example, some of these down here would turn on, and some of these at the end would receive that signal that these ones would send. So these would turn on, sending a signal. That signal would reflect off of, well, it would travel through underground bodies and would be received by these back here. These would send data back into the machine and tell us how resistive the underground bodies are. The next survey that we did was a GPR survey. And what the GPR survey does is similar to what the resistivity survey does. It sends a signal into the ground and receives that same signal. With the GPR survey, instead of sending electricity, it sends a laser down to the ground. And this is great because it helps us detect buried objects and subsurface bodies that are solid. So for example, detecting the drainage pipes underground is very helpful and useful with the GPR survey. The GPR survey setup consists of a computer console, which is up here, which is the brains of this survey. It collects data and information and processes it for us to be able to interpret underground or subsurface features. We also have the transmitter, which sends in a laser into the ground, which then reflects off of certain bodies and is picked up by the receiver. This whole survey works great, but an odometer is very, very helpful with calculating distance. So that way we can actually create a cross-section for our computer console to interpret. And so the odometer basically is connected or related to one of these wheels here. And as this wheel turns, the odometer picks up how many rotations per minute this cart is going and therefore translates that into distance. And then of course we have our cart here, which carries everything and transports it along the way. As far as data acquisition and processing goes, I was not able to complete this on my own. I depended on the NKU faculty for this part of my project because I lacked the software and the knowledge of how to use the software to make any interpretations or processes on my own. And here we have the results of our resistivity surveys. We don't really have much resistive material down here underground, as well as we don't have too great of a depth. We go down to 2.68 meters, which is a good depth, but for being on a hill, we could go deeper. Here's another image of the resistivity survey that I did. This is a second survey, rather, that I did. And this is very similar visually to the one that we just looked at. And that's because these were done at the same exact positions on the same day at the same exact, nearly the same exact time, one right after the other, which is great because it helps us cancel out a lot of variables that might happen with, like, you know, day to day, different changes that might happen in this area, which is great that we're able to do this one day and kind of have some consistent information. So for the GPR surveys, this one was a little more difficult. This survey up here is the survey of the entire hill. Meanwhile, this is only of the upper portion that we did the resistivity survey on. And the other issue that we had was that this survey was not taken at the same exact location that this one was. This one was offset by just a couple inches, or about a foot. And the problem with that is that because they were done on different days, we weren't able to get exact perfect data. As you can see over here, we don't have really many physical shadows, but we do here. And that's because this resist GPR survey had gone over top of some of the sewage lids and some of their drainage pipes. So we get these big giant shadows here, which is great because that means that GPR system is working. We're able to detect the bodies on the surface, but we want to detect if there's any bodies underground. And this causes a couple issues with that by keeping us from being able to make those interpretations. With the limited data that I had, I made an interpretation of this survey. According to my resistivity surveys, this area was made mostly of siltstone and claystone, so there really wasn't much to worry about in this area. I noticed that there were no metal drainage pipes, which is great. I know that now my cores more than likely won't hit anything of value or importance or expense, which is awesome. There was no groundwater though, which is as we expected. So ultimately, this supports my hypothesis and my conclusion that there are no detectable drainage pipes or groundwater in this area. Some of the errors I ran into on this survey were, of course, the different dates that I had taken this my surveys. The resistivity surveys were all on the same day, the same location. You know, the ground was very dry, so we were able to get good images. But the GPR surveys did not go nearly as smoothly. They were taken at many different dates because of the precision needed for this survey. Being offset by just a couple, just by a foot or so, caused an issue with exact locations of the data collection. And then one of my GPR surveys was taken just a few days after a light rain shower, which is why one of my surveys seems kind of more difficult to interpret than the other, because one of them is kind of more blank while the other one's has more defined lines. I believe the weather probably had something to do with that. But ultimately, I believe that the greatest error, or one of the greatest issues with my survey, is of course the depth. Because our surveys only go to such a shallow depth, I'm not able to record or identify any pipes that may go beyond 10 feet or beyond 20 feet. And the same thing goes with the GPR survey. Being a shallow survey, I'm not able to get very good depth. And so those are some of the errors that I have with my resistivities, with my surveys as a whole. And that is my presentation for my survey project for my Geology 360 class, Geophysics. Thank you very much for listening.